Hello and welcome to ALEK's walkthrough video number 5. My name is Robert McKeown and today we're going to be talking about functions and graphs. Students, in my experience at York University, and I've not been here very long, students find this topic extremely challenging. I don't think it's particularly hard, but what you have to do is you have to memorize a number of definitions and then apply those definitions to different situations. And that can be a little bit difficult because you actually have to learn the definitions. You actually have to do the work. Doesn't matter how smart you are. Smart is not going to help you if you don't have the knowledge necessary to answer the question. And so this is actually the longest series of videos of all 8 topics because there's just so much that I want to explain to you and that you just need to know. So you can think of maybe the first 4 topics as being rather introductory, didn't require a lot of background knowledge. Now we're building off the knowledge you learned in topics 1, 2, 3, and 4, and we're going forward into more advanced mathematics and into economic applications. So again, before we get started, make sure you have a pencil, a pen, paper, or if you're really fancy, get yourself a tablet with a writing pen. That's a really great tool to have. I was so impressed with my students who had one that I went out and bought one. And I use it in class. If you've ever had a lecture with me, you'll see it for sure. So, without any further ado, let's get down to the problems. To answer the topic 5 questions correctly, you have to understand a few definitions. And our first definition is what is a function. So you can read a formal definition on the slides. One thing I'd like you to think about is I'd like you to think about a street light. So functions don't have to be mathematical in nature. We could have an x variable, which is the street light can be a red light, can be red, or it can be a green light. And there's a function that transforms that observing that light into an outcome, which is stop your car for the red light, and if it's a green light, it's go. And so we've got 2 ordered pairs here. We've got an ordered pair that's red light and associated with stop, and another ordered pair that's a green light and it leads to go. So that's an example of a function in everyday life. We're going to focus on numerical functions here, but in economics, sometimes we don't want to use numbers. We want to use concepts like this, and we do so. Here is another definition, maybe a simpler definition of what a function is. So we've got a function, something like this, and we might have y is equal to some function of x. So let's consider a function x squared. So if x is equal to 0, y is going to also be equal to 0. And if x is equal to 1, y will be equal to 1. If x is equal to -1, y is also equal to 1. And so I'll tell you that x squared is a function for every x there is 1 y value. Now I haven't proved it, but if you want, you can go home, you can put in any number you want into that, and you're only going to get one y value. Whatever number you put into that function, you're going to get only one y value. In fact, that's what makes it a function. Let me show you an example of something that is not a function. So this is a function. What if I have, I can't use that terminology. What if I have y squared plus x squared is equal to 25? Well, I've got y is equal to a function of x, so why don't I rearrange this thing over here and isolate y on one side so that it looks like the function I showed you on the left-hand side of the screen. So I can take, I know that y squared is going to be equal to 25 minus x squared. I can write y, I'll take the square root of both sides of the expression. So I've got 25 minus x squared. But notice that this is going to be plus or minus. Whenever I take the square root of something that's been squared, it could be positive or negative. And so with this example, for each x value, there are two possible, I'm not going to say each, I'll just say for some. There are two possible y values. So it's not a function. The language we like to use in mathematics and economics is that the x values are in something called the domain, and the y values are in something called the range. So if I've got a set of x's here, and maybe I've got 1 or 0, 1, and 2 here, this is the domain. And then there's some function that takes us to in fact, I'm going to just change this one to a -1, like in our previous example. And -1 also maps to y equals 1. So the function is mapping from the domain into the range. And if you want to read more about it, I found a neat website down here that you can read more about domain and range and what a function is and what a function is not. There is a special kind of function, and it's called a one-to-one function. Now, when we had this previous example, we had a function that was equal to x squared. But you can see here that, and I'll get rid of that because we don't care about it, but you can see that there's more than one x value. In fact, there are two that lead to one y value. So this is not a one-to-one function. Now let me see. I could write a one-to-one function which is just f of x is equal to x. And notice that each number in the domain leads to a unique number in the range. So f of x equal to x is a 1-to-1 function. So this is a function over here, but it's not a 1-to-1 function. It's a function, but not a 1-to-1 function over here. This is a function, and it is a 1-to-1 function. One-to-one functions are important because every one-to-one function has an inverse function. So let's consider another one-to-one function. I'll have 0, 1, and 2 in my domain. And this time I'll just say let the function be equal to 2x. And there's my domain. And I'm going to have y values here. If x is 0, y is 0. If x is 1, y is 2. And if x is 2, if x is 2, y is 4. Now let's consider the inverse. So if we have the inverse of this function's unique inverse, then it's going to reverse. It's essentially just going to reverse the mapping. And the inverse of this function is equal to 1/2 times x. So inverse functions are not very, very complicated in their fundamental or simplest form. They're just reversing where we're moving from. Are we moving from x to get y, or are we taking y to get x? Inverse functions have a very interesting property. So this little operator here creates a composite. So this is a operator to create a composite function. And more commonly, it's written like this, which is basically to say that if we have the inverse function and we plug it into the original function, we're going to end up with just x, whatever that x value is. So let me give you an example from the previous one. We had f of x is equal to 2. The inverse of that function, or excuse me, that was 2x. The inverse was equal to 1/2 x. And say I wanted to evaluate we always start with the inner, right? Whatever is in the brackets is the first order of operations. So f inverse 3 have 1/2 times 3, which gives us 3/2. Now let's take that 3/2 and plug it into the original function, and we get 2 times 3/2, which is equal to 3. And that is exactly what this special property is all about. And it says that if we take the inverse of x, and then we take that inverse of x and take the function of the whole thing, we get x. We've gone through an introduction together. Let's apply what we've learned to answer the next 3 questions. So we're given 2 functions. The first function g doesn't have any calculations. It's just a set of ordered pairs. So giving us the ordered pairs directly. We don't have to do any calculation to find them. The second function, h, is a function as you're used to seeing it, where we're going to have to perform some calculations. Now the first question is asking us to find the inverse of g. So remember that if we have x mapping into y according to g, now we've got the inverse of g where we're mapping from y to x. So g inverse is going to take the y value here, move it to the first position where the domain is, and if y is equal to 7, we're going to map to x equal to -5. And we're going to do that for each of the ordered pairs. And the squirrely bracket represents a set, beginning and the ending of the set. And it's a set of ordered pairs. And we're done. So finding the inverse function when you're given a set of ordered pairs is very straightforward. You just switch the positions of the domain and the range. So we're asked to find the inverse of h of x. So I'm going to start it off by writing y is equal to 3x plus 13. And now I'm going to solve for x. So I'm going to isolate x on the left-hand side of the equation. So I'm going to have 3x is equal to y minus 13. And then x is equal to y minus 13 divided by 3. Then I'm going to replace x with y and y with x. So I'm going to have y is equal to x minus 13 over 3. So the inverse is equal to x minus 13 over 3. So that's the inverse of the function. So sort of switching the x's and y's around, but that's just because we want to show the inverse function should be a function of x. Our next question is asking for the composite function h, composite with its inverse. And it wants us to evaluate that composite function when x is equal to 4. So why don't I do this the hard way, and then I can show you and remind you how to do it the easy way. So another way of writing this is to say that we have h inverse of 4, and then that inverse is actually within the original function. I've taken the inverse function we came up with on the previous slide and brought it with me. And so why don't we do that one first? So h1 of 4 is going to be equal to 4 minus 13 divided by 3, which is equal to negative 9 over 3, which is equal to negative 3. Now I'm going to plug that negative 3 into the original function. 3 times negative 3 plus 13 is equal to negative 9 plus 13, which is equal to 4. Right? And that's exactly what we should get, because we know that the composite of the h function and its inverse, I'll delete that little x, when it's evaluated at 4, or whether it's x, is going to be equal to 4. Right? And just like if we didn't have a number to evaluate it at, we would get